From the dawn of humankind we have gazed up at the stars and wondered. The night sky, a tapestry of twinkling light, has inspired countless myths and stories. The quest to understand our origins has captivated philosophers, theologians, and scientists for centuries. The Big Bang Theory, born from the brilliant minds of physicists and astronomers, paints a picture of a universe emerging from a state of unimaginable density and heat. This tiny point, this cosmic seed, exploded with unimaginable force some 13.8 billion years ago. As the universe expanded, it cooled, allowing for the formation of the first elementary particles, the building blocks of all matter. One of the most compelling pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, the afterglow of the Big Bang. This faint, uniform glow of microwave radiation permeates the entire universe and is thought to be a relic of the intense heat and energy present in the early universe. Discovered in 1964 by astronomers Arno Penzias and Robert Wilson, it provided the first direct observational evidence for the Big Bang Theory. The discovery of the cosmic microwave background radiation marked a turning point in our understanding of the universe's origins. Scientists continue to explore the mysteries of the Big Bang, using increasingly sophisticated telescopes and instruments to probe the farthest reaches of space and time. The quest to understand our cosmic origins has taken us from myth to the forefront of scientific discovery. Imagine a balloon with dots scattered across its surface. As the balloon expands, the dots move farther apart. This simple analogy helps us visualize the expansion of the universe. Edwin Hubble's observations in the 1920s provided the first concrete evidence that the universe was in a state of constant expansion. This discovery laid the groundwork for the Big Bang Theory, supporting the idea that the universe had a beginning. The expansion of the universe is not uniform, it is accelerating. This discovery, made in the late 1990s, came as a surprise and has profound implications for our understanding of the universe. The expansion is driven by a mysterious force known as dark energy, which makes up roughly 70% of the universe's total energy density. The nature of dark energy remains one of the biggest mysteries in modern cosmology. According to the Big Bang Theory, the universe began as an extremely hot, dense, and rapidly expanding singularity. As the universe expanded and cooled, the forces of nature began to separate and take on their distinct identities. Gravity, the weakest but most far-reaching of the fundamental forces, was the first to emerge. The separation of these forces marked a critical transition, paving the way for the formation of the first particles. In the first few minutes after the Big Bang, the universe was a seething cauldron of energy and elementary particles. As the universe continued to expand and cool, protons and neutrons combined to form the first atomic nuclei. Hydrogen and helium, the two most abundant elements, would later provide the raw materials for the formation of stars and galaxies. The Big Bang Theory, while dominant, isn't the only explanation for the universe's origin. The steady-state theory, popular in the mid-20th century, proposed an eternal and unchanging universe. While the steady-state theory is no longer widely accepted, it serves as a reminder that scientific understanding is always open to revision. The concept of a cyclical universe proposes that our universe is part of an endless cycle of expansion and contraction. One such model is the ekpyrotic universe, suggesting our universe collided with another hidden dimension, triggering the Big Bang. While intriguing, cyclical models face significant hurdles, such as the lack of observational evidence for a contracting phase. The multiverse theory proposes that our universe is just one of many coexisting within a higher dimensional space. These universes could have arisen from quantum fluctuations in the primordial universe. While highly speculative and currently untestable, the multiverse theory pushes the boundaries of our imagination. The quest to understand the universe's origin is woven into the very fabric of human curiosity. Ancient civilizations gazed upon the celestial tapestry, weaving their observations into myths, legends, and philosophies. The transition from myth to scientific inquiry was gradual, marked by both intellectual leaps and periods of stagnation. The work of Islamic scholars during the Islamic Golden Age proved crucial in preserving and advancing astronomical knowledge, laying the groundwork for the Renaissance in Europe. The European Renaissance ushered in a new era of scientific exploration. Nicolaus Copernicus proposed a heliocentric model, challenging the geocentric view. This idea sparked a paradigm shift in our understanding of the cosmos. Johannes Kepler's laws of planetary motion described elliptical orbits. Kepler's work paved the way for Isaac Newton's theory of universal gravitation. Newton's law of universal gravitation revolutionized our understanding of the universe. His work unified celestial and terrestrial mechanics. The development of the telescope marked another significant milestone. Galileo Galilei used the telescope for astronomical observations. His discoveries supported the heliocentric model. By the early 20th century, astronomers had amassed a wealth of data about the stars and galaxies that populate the cosmos. However, the question of the universe's origin remained shrouded in mystery. Was the universe static and eternal as many believed, or did it have a beginning? The answer to this fundamental question would come from an unexpected source: the study of distant galaxies. Edwin Hubble, an American astronomer using the powerful Hooker telescope at Mount Wilson Observatory in California, made a series of groundbreaking observations that would revolutionize our understanding of the universe. By studying the light from distant galaxies, Hubble noticed a peculiar pattern. The light was stretched, its wavelength lengthened, a phenomenon known as redshift. Hubble realized that this redshift was not due to the motion of galaxies through space, but rather to the expansion of space itself. Just as dots on an inflating balloon move farther apart, galaxies are moving away from each other because the fabric of space is stretching. This discovery, announced in 1929, shattered the long-held belief in a static universe and provided the first observational evidence for an expanding cosmos. Hubble's observations had profound implications for our understanding of the universe's origin. If the universe is expanding, then it stands to reason that it must have been smaller and denser in the past. Extrapolating backward, this expansion suggested a point in time when the universe was infinitely small and infinitely dense, a concept that would later become known as the Big Bang. The Big Bang theory, while gaining traction, lacked direct observational evidence. The smoking gun, a relic of the universe's fiery birth, would come in the form of a faint afterglow permeating the cosmos, the cosmic microwave background radiation. This faint, uniform glow of microwave radiation, discovered serendipitously in 1964 by Arno Penzias and Robert Wilson, provided the first direct observational evidence for the Big Bang. Penzias and Wilson, working at Bell Telephone Laboratories, were using a sensitive microwave antenna to study radio signals from space. To their puzzlement, they detected a persistent background noise that seemed to come from all directions. This noise, initially dismissed as interference, turned out to be a faint echo of the Big Bang, a remnant of the intense heat and energy present in the early universe. The cosmic microwave background radiation provides a snapshot of the universe as it was just 380,000 years after the Big Bang. At that time, the universe had cooled enough for protons and electrons to combine into neutral atoms, allowing light to travel freely for the first time. This first light has been traveling through the universe ever since, carrying with it a wealth of information about the early universe. Since its discovery, the cosmic microwave background radiation has been studied in detail by a series of increasingly sophisticated space missions, including the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite. These missions have mapped the temperature and polarization of the cosmic microwave background radiation with unprecedented precision, providing insights into the age, composition, and geometry of the universe. The quest to unravel the universe's origin is a testament to human curiosity. Scientists like Edwin Hubble and Georges Lemaître have shaped our understanding of the cosmos. Hubble's observations revealed an expanding universe while Lemaître proposed the Big Bang theory. Their legacy continues to inspire scientific exploration. Edwin Hubble's journey began in academia, not under the night sky. Armed with a law degree, he initially pursued legal practice, but his passion for astronomy was too strong to ignore. He earned his doctorate in astronomy in 1917. After World War I, Hubble joined Mount Wilson Observatory, home to the 100-inch Hooker telescope. Here, Hubble revolutionized our understanding of the universe. Observing distant galaxies, faint smudges of light, the nature of these spiral nebulae was debated. Were they gas clouds or distant galaxies? Hubble's observations provided the answer. In 1923, he observed the Andromeda Nebula, identifying a Cepheid variable star. These stars pulsate with regularity. Comparing brightness, he calculated its distance, proving it lay beyond the Milky Way, confirming other galaxies. While Hubble was busy mapping the expanding universe, a Belgian priest and physicist named Georges Lemaître was grappling with the profound implications of Einstein's theory of general relativity. Lemaître, ordained as a priest in 1923, had also pursued advanced studies in physics, earning his doctorate from the Massachusetts Institute of Technology in 1927. His unique blend of scientific and theological perspectives led him to ponder the ultimate origin of the universe. Intrigued by Einstein's equations which describe the relationship between gravity and the geometry of space-time, Lemaître realized that they allowed for a universe that was not static but rather dynamic, either expanding or contracting. In 1927 he published a paper proposing that the universe had originated from a single incredibly dense and hot state, which he called the primeval atom. Lemaître's idea initially met with skepticism from some of his contemporaries, including Einstein himself, suggested that the universe had a beginning, a moment of creation. This radical notion, challenging the prevailing view of a static and eternal universe, laid the groundwork for what would later become known as the Big Bang theory. Lemaître's primeval atom concept provided a theoretical framework for understanding Hubble's observations of an expanding universe. If the universe was once a single point, as Lemaître suggested, then it made sense that galaxies would be moving away from each other as space itself expanded. Lemaître's work, a testament to the power of combining scientific rigor with philosophical inquiry, paved the way for a new understanding of the universe's origin story. The Big Bang theory explained the universe's expansion, but faced challenges like the horizon and flatness problems. Why is the cosmic microwave background radiation so uniform? How could distant regions reach thermal equilibrium? Why is the universe's geometry nearly flat? In 1980, Alan Guth proposed cosmic inflation to solve these puzzles. The universe expanded exponentially, driven by the inflaton field. This smoothed out irregularities and explained the universe's flatness. Guth's theory is now a cornerstone of modern cosmology. Our exploration of the universe's origins, from the fiery chaos of the Big Bang to the elegant dance of galaxies across the cosmos, reveals a profound truth. The more we discover, the more we realize how much remains unknown. The universe, with its vastness and complexity, holds its secrets close, yet each tantalizing clue we uncover pushes back the boundaries of our understanding, revealing a cosmos far grander and more mysterious than we ever imagined. The Big Bang Theory, while our best current explanation for the universe's beginning, is not a complete story. It leaves many questions unanswered, inviting us to delve deeper, to refine our models, and to seek new observations that can illuminate the universe's earliest moments. What, if anything, existed before the Big Bang? What caused the universe to inflate so rapidly in its first fraction of a second? These are just a few of the questions that keep cosmologists awake at night, driving them to explore the universe's hidden depths. The search for answers takes us to the frontiers of scientific inquiry, to the realm of particle accelerators that recreate the extreme conditions of the early universe, to the depths of space where telescopes peer billions of years into the past, capturing the faint light from the universe's infancy. Each new observation, each theoretical breakthrough, brings us closer to understanding the universe's grand narrative, a story that began billions of years ago with a burst of unimaginable energy and continues to unfold before our very eyes. As we stand at the precipice of the unknown, humbled by the universe's immensity, we are confronted with a profound realization. The quest to understand our cosmic origins is an ongoing journey, one that may never truly end. For every question we answer, new questions arise, each more challenging, more awe-inspiring than the last. The nature of dark matter and dark energy, two of the most perplexing mysteries in modern cosmology, continues to elude us. Dark matter, an invisible substance thought to make up roughly 85% of the universe's matter, interacts gravitationally but remains invisible to our telescopes. Dark energy, a mysterious force driving the universe's accelerating expansion, challenges our understanding of gravity and the universe's ultimate fate. The search for life beyond Earth, another tantalizing frontier, fuels our imaginations and underscores the interconnectedness of cosmic phenomena. The ingredients for life, forged in the hearts of stars and scattered across the cosmos, suggest that we may not be alone in the universe. The discovery of even a single microbe on a distant planet would revolutionize our understanding of life's origins and our place in the cosmic tapestry. The universe, with its boundless capacity to surprise and amaze us, holds countless secrets waiting to be unlocked. As we continue to explore, to question, and to marvel, we embrace the unknown not with fear but with a sense of wonder and anticipation, knowing that the greatest discoveries are often those we least expect. The story of the universe's origin is not merely a scientific tale, it is a story about us, about our place in the grand scheme of cosmic evolution. We are, after all, made of star stuff, the products of billions of years of cosmic evolution, from the fiery crucibles of the Big Bang to the gentle caress of starlight on a distant planet. As we contemplate the universe's vastness and our own fleeting existence within it, we might be tempted to feel insignificant, lost in the immensity of space and time. Yet there is also profound beauty in this realization, a sense of awe and wonder that connects us to something far greater than ourselves. We are the universe becoming aware of itself, the cosmos contemplating its own existence through our eyes, our thoughts, our dreams. Our quest to understand the universe's origin is a journey of self-discovery, a way of unraveling the threads that connect us to the cosmos, to the very fabric of space and time. It is a journey that transcends scientific inquiry, touching upon our deepest philosophical and spiritual yearnings. As we explore the universe both within and beyond ourselves, we embark on a profound adventure, one that challenges our assumptions, expands our horizons, and ultimately leads us to a deeper appreciation for the beauty, complexity, and interconnectedness of all things.